Photoelectric effect. Hertz noticed that the sparks occurred in the air gap of his transmitter when the ultraviolet light was directed at one of the metal balls. The electrons emitted when the frequency of light was sufficiently high. This phenomenon is known as the photoelectric effect, and the emitted electrons are called the photoelectrons. The evacuated tube. This evacuated tube contains two electrodes, which is connected to variable source with the metal plate whose surface is irradiated as the anode. Some of the photoelectrons that emerge from this surface that have the enough energy to reach the cathode, even though it is negative polarity, the electrons reach at the cathode, which have the high sufficient energy and produce the photoelectric current. The slower photoelectrons are repelled before they get into the cathode. When the voltage is increased to a certain value V0 of the order of several volts, no more photoelectrons arrive, as indicated by the current dropping to 0. This voltage corresponds to the maximum photoelectron kinetic energy. Okay, the three experimental findings show that no such simple explanation is possible. It cannot explain by in a simple way. Why? Because of these three experimental findings. The first one is experimental accuracy is 10 raised to minus 9 second. Okay, and there is no time interval between the arrival of light at a metal surface and emission of the photoelectrons. So there is no time interval between the arrival of light at the metal and the emission of the photoelectrons. A detectable photoelectron current result is 10 raised to minus 6 watt per meter square of EM energy is absorbed by the sodium surface. A layer of sodium 1 atom thick and 1 meter square in area contains around this much atom, 10 raised to 19 atoms. So if the incident light is absorbed in the uppermost layer, each atom receives energy at the average rate is 10 raised to minus 25. At this rate, over a month would be needed for an atom to accumulate the energy. At this rate, over a month would be needed for an atom to accumulate the energy of the magnitude that photoelectrons have. But here, it is happen very quickly. There is no time interval between the light arriving at the metal surface and the emission of photoelectrons. So how can uh, give the explanation for this? So that is one problem. Other problem is bright light yields more photoelectron than a dim light, but the frequency is same, but the electron energy remains the same in figure A. So in figure A is showing the retarding potential. It means it's nothing but like stopping potential. Stopping potential is to stop the electron ejecting from the metal surface when the incident beam energy is greater than the work function of the metal. Okay, so this is retarding potential and this is photoelectron current. So here we can see it's changing the intensity. If we changing the intensity, photoelectron current is changed. We increase the retarding potential, it goes to met the V0. Here we have already given the certain value of V0. right? Frequency is constant when intensity is changing, so photoelectron current change. Similarly, if the light intensity is constant, but if we change the frequency nu1 to nu2 to nu3, this is highest one, lower, and again more lower, but the current is same. So current is like is a constant. If you increase the frequency, current will not change. Okay, from this is not explained by electromagnetic theory of light. This is contrary, predicts that the more intense the light is, the greater the energy is. Because in the electromagnetic theory, it assumes if it is more intense light, that the energy of the electron is high. But it's contradictory with argument with the EM theory of the light. But the third problem, like this is the third problem is higher the frequency of the light, so more energy of the photoelectrons, yes, but the photocurrent is the same. At the frequency below certain critical frequency mu 0, which is characteristic of each particular matter, no electrons are emitted. No electrons are emitted here. No electrons are emitted. But this is the threshold frequency. Then only electrons will emitted. Above mu 0, the photoelectrons range in energy from 0 to a maximum value that increase linearly with increasing the frequency. Figure C, like this: cesium, sodium, calcium. This observation also cannot explain by the EM theory of light. So this three explanation could not be explained by the electromagnetic theory of light. That's why Einstein explained it in a very simple way. So that the theory is quantum theory of light. What Einstein explained? Einstein told the photoelectric effect could be understood if the energy in light is not spread out over the wavefront. It is not a spread out over the wavefront, but it is a concentrate in a small packets. That packets means photons. Okay. Here the Einstein gives very simple explanation of these three problems. The first one, because of electromagnetic wave energy is concentrated in the photons and not spread out, there should be no delay in the emission of the photoelectrons. So we know that the first problem is the incident uh, light when strike the metal and the photoelectron is emitted. The interval between two is there is no interval between the two phenomena. So Einstein explained very simple. The since it's concentrate photons and it is not spread out, that's why there should be no delay in the emission of the photoelectron. Another statement he explained, all photons of frequency have the same energy. So changing in the intensity of the monochromatic light beam will change the number of photoelectrons but not their energy. That's why here we'll change the number of photoelectrons. We'll change the number of photoelectrons, that's why the photoelectron current will change. But the frequency is same. The third one, the higher the frequency, the greater photon energy h nu. The higher the frequency, the greater photon energy h nu. So more energy of the photoelectrons have. That's why the critical frequency mu 0, below which no photoelectrons are emitted. There must be a minimum energy phi for an electron to escape from a particular metal surface. This energy is called the work function of the metal, which is related to mu 0 by the formula. the work function phi is equal to h nu 0. The greater the work function of the metal, more energy is required for an electron to leave its surface, and higher the critical frequency for photoelectric emission to occur. So here a higher frequency is required to escape the electron from the metal surface. According to Einstein, he suggests the equation h nu photon is equal to maximum kinetic energy plus work function. H nu is photon energy, maximum kinetic energy or the maximum photoelectron energy, which is proportional to the stopping potential, and phi is the minimum energy which is needed to electron leave from the metal. Figure D. This is the figure D. So here it is h nu 0, then the kinetic energy is 0. When photon strike on the metal, the electron will leave the metal surface. So that's why maximum kinetic energy is equal to h nu minus h nu 0. So h nu is equal to kinetic energy plus work function phi. So kinetic energy h nu minus h nu 0. So h nu minus nu 0. This formula accounts for the relationship between the maximum kinetic energy of the photon, which is plotted in figure C from the experimental data. If the Einstein, or sorry, plotted in figure C from the experimental data, this one. If the Einstein was right, the slope of the line should all be equal to the Planck's constant, and it's really equal to the Planck's constant. This is indeed the case. Means if you take the slope of this line, it's exactly same to Planck's constant. Means Einstein was right. Here the explanation of this figure: if the energy h nu 0, the work function of the surface is needed to remove the electron from a metal, the maximum electron kinetic energy will be h nu minus h nu, where the light of the frequency is directed at the surface. So here is the photoelectron effect complete.